In this part of section 13.1, we're looking at the graph of a function of two variables. The graph of a function of two variables is the set of all points in space, x, y, z, for which z is equal to f of xy, and xy is in the domain of f. Here, our graph of the function is the points in space. In this case, those points represent a surface. Let's find the range of f of xy equals the square root of 16 minus 4x squared minus y squared. Now you can think about this in terms of what are all the possible values that you can get out of this function. The smallest that x and y could be is 0. So the largest that this could be is the square root of 16, which is 4. And then when you're talking about square roots, if 4x squared minus y squared was equal to 16, you would get the square root of 0. So we're going to be looking at a range somewhere between 0 and the square root of 16. But let's look at this in more detail. The domain is a set of all points where this part underneath the square root has to be greater than or equal to 0. By rearranging using some algebra, we can find that the domain is all the points lying inside the ellipse given by x squared over 4 plus y squared over 16 equals 1. This is an ellipse in the plane. So to determine the range would be looking at all the values that you get out, such that 0 is less than or equal to z, which is less than or equal to 16. So the range of z is between 0 and 4. To graph it, you can rewrite the function z equals the square root of 16 minus 4x squared minus y squared. We're simply replacing the f of xy with z. And if you look at it this way, square both sides, and rearrange the terms, it begins to look like one of those quadric surfaces back in chapter 11. If you recognize a surface, you will see that it's an ellipsoid. But the original function was just the square root, which would represent the top half of the ellipsoid. So we can write it in this way. The range is everything from 0 to 4. And when you sketch it, here the domain is everything within that ellipse, and the range is everything that you get out, and the surface is the top half of an ellipsoid. So you can see the lowest that the ellipsoid goes is 0 on the z-axis, and the highest that the ellipsoid goes is 4 on the z-axis. So that's a way of looking at the range graphically. A second way to visualize a function of two variables is to use a scalar field in which the scalar z equals f of xy is assigned to the point xy. And the previous example required looking at graphing. Graphing 3D surfaces by hand can be kind of tricky. So this is a way to represent a 3D surface with a two-dimensional depiction. A scalar field can be characterized by level curves or contour lines, along which the value of f of xy is constant. For instance, the weather map in this figure shows level curves of equal pressure called isobars. Here you can see kind of an outline of the United States, and this is a typical map that you would see on the Weather Channel. The lines that are connected, they connect equal pressure. And the closer those are together, the bigger the change, or the quicker the change in pressure. So you would end up with a very windy situation with these very close isobars. Here's an example I'd like to show you that has, well, let's just take a look. Now if we click on this link, we get some options here. What we have here is a graph of a function of two variables. It's a surface, and unless you're using technology, this will be very difficult to do by hand. So let's try to figure out a way that we can look at this surface, this 3D surface, but represent it in a two-dimensional way. In this case, you can rotate the graph a little bit and see kind of it has a couple hills and valleys. And what this link is going to show you is how we can create those contour lines. So you're taking the surface and imagine that you're slicing it horizontal to the XY plane. Those slices create traces or contour lines. Those contour lines are graphed on a two-dimensional graph. This is a 3D graph sliced at these equidistant elevations, if you will, and then those traces where those slices connect with the 3D surface, you're going to be creating those contour lines. When you do that, those traces, when you start to look at them in a two-dimensional graph, just from above you see that we have the two-dimensional graph that shows those the pattern where the elevation increases and the elevation decreases. Again, this was the original surface we're looking at, and by slicing it at different elevations and figuring out where the slices intersect with the surface, you create those contour lines. Okay, in this case, we're looking at a weather map again. The level curves represent points of equal temperature. The level curves are called isotherms. Again, another weather map here. You see about 70 degrees on this line, 80 degrees around here. These are connecting the equal temperatures called isotherms. Another common use in level curves is representing electric potential fields. In this type of map, the level curves are equipotential lines. Here's another example of level curves. Contour maps are commonly used to show regions on the Earth's surface. You look at a map, you don't see, it's not three-dimensional, it's a flat piece of paper. But the lines give you the representation of the three-dimensional surface. The level curves representing the heights above sea levels. This type of map is called a topographic map. For example, the mountain shown on the left is represented by the topographic map on the right. Now take a look at this. Is actually the Half Dome at one of our national parks. I believe it's Yosemite. Oh. And you can see this is a great place if you want to go rock climbing because the side of this mountain is very, very steep. And then the other side, it's pretty steep, but as you can see on the top, not as steep. And as you get further away from the top of the mountain, very, very steep, definitely very steep on this side. And in fact, the closer those lines are together, the steeper the descent, because those are connecting lines of equal elevation. And if those are farther apart, then the elevation doesn't change as rapidly. If they're very close together, there is a quick change in elevation because those lines are so close together. Here's an example of sketching a contour map. The hemisphere given by f of xy equals the square root of 64 minus x squared minus y squared is shown in figure 13.9. Sketch a contour map of this surface using level curves corresponding to c equals 0, 1, 2, all the way up to 8. Now it is important that these level curves are equidistant in terms of you want the same increase in elevation each time. You don't want to increase by 1 the first time and then up to 3 the next time. You want them to be equally spaced out in terms of the z elevation. So you're going to set the function equal to each of these elevations to determine the contour lines or the level curves. You can see it's sliced at c equals 0. The slice of the surface is the largest circle. At c equals 1, the circle's not quite as large, and as the elevation increases, the circles, which are the contour lines, get smaller. When you set the function equal to 0 and rewrite it, you get x squared plus y squared equals 64. That's your circle of radius 8. And you set each time you do this, you set the original equation equal to each of those c levels. As c equals 0, you get the circle with radius 8. As c equals 1, you get a slightly smaller circle, c equals 2, 3, 4, and so on, all the way up to c equals 8. When the elevation is 8, the intersection is simply a point. Now, in terms of how steep the surface is, you can see as the contour lines are closer and closer together, you have a steeper portion of the surface. These contour lines are further apart, it's not as steep.